failed. That was that cheap old Walmart brand. So we're going to pay a little more now for the more expensive brand, right? Okay, so we're going to take the limit now as n goes to infinity. Oh, by the way, this one right here did what? Converged, right? That converged. So we're comparing, our series is being compared to a p series, p being 2, it's convergent, but we're using the limit comparison test instead. So we do a sub n over b sub n. Bam, bam. There's a sub n over b sub n. Flip, right? Yep, multiplied by the reciprocal. And you get n squared over n squared minus 2n. And I think that would qualify for L'Hopital, right? After we switch them to functions of x. But we're going to stop switching them to functions of x because it's going to take too much time.
So is it fine?
Yes, on the test it's fine at this point. You can just go straight to L'Hopital. But with the understanding, like there's a little asterisk here, with the understanding that we are actually going to functions of x. So what would it be under L'Hopital here? 2n over 2n minus 2. So we got to run L'Hopital again, one more time. So limit n goes to infinity, L'Hopital 2 over 2, which is 1. Now, is 1 a positive constant? Absolutely. So what does this tell us? Whatever that one does, they both do. And one of them converges, so the other one must also converge. So they converge. Isn't that a nice test? Isn't that a nice test? Therefore, the conclusion is that 1 over n squared minus 2n converges. Bam. This has to be a positive constant. It cannot be infinity and it cannot be 0. If it's 0 or infinity, then our expensive pregnancy test failed too. You know what I'm saying? All right, we good? Y'all feeling all right about that? Let's do the other one that caused a problem. What was the other one that caused a problem? The one that we were going to do n to the 5th.
N plus 5.
That's right. Okay, n plus 5 over
The 5th root of n squared plus 2n plus 1.
Okay, so that we had stopped because nobody here wanted to do n plus 5 to the 5th power, right? Which I'm on board with that. I don't feel like doing that either. So we're going to go back to that one. What was it that we compared it to?
1 over n.
Yeah. So we compare this. We're comparing it to this one. I think I said I wanted to leave it unsimplified, right?
Yeah.
That does become the whatever it was, right? Was that convergent or divergent? This was divergent, right? So we are comparing this series to a divergent series. So I'm not putting all the work here again, right? P series, P is what, 3/5 or whatever it was, 2/5. I'm not showing that. We're just going to go to this. So I'm using limit comparison. Okay, limit comparison. I'm going to take the limit as n goes to infinity of the a sub n, which is this ugly one, over b sub n, right? Over this one? But when I put it over this one, I'm going to really multiply by the reciprocal. So is it okay if I go ahead and do that now? And just times it by the 5th root of n squared over n. Is that all right if I do that instead of doing a sub n over b sub n? Now, when you look at that initially, you might be like, oh, I don't know what I'm going to do with that. But like, you don't want to do L'Hopital on that, right? But just tell me if you agree with this. We'll do it like this. Is that the same thing? This is the fifth root on that. So all I did was, it's multiplication, so I slid things around, right? So I like flipped the order of those. So I put that over, these n plus 5 over n, right?
Yeah.
And then these are both fifth roots, aren't they?
Yeah.
So I can do one big fifth root and then put the 2 in there. That's the same thing. And now the great thing about the limit is that the limit can go inside. So I can do the limit of this one separately. I can take the limit inside here and take that limit and then take the fifth root of that answer. So what is this? What is this limit right there? So infinity over infinity? You can do a little L'Hopital on that. You just get 1. And then here, you'll get infinity over infinity. You do L'Hopital, you get 2n over 2n plus 2. L'Hopital again, you get 1 again. Right? You get the fifth root of 1. Fifth root of 1, which is 1. So this is 1. This is a positive constant. So whatever they do, they both do. Diverge.
And you said because they're multiplying like that, you can take the limit separately?
Yes. Yep. So we have a property about limits that says the limit as whatever goes to whatever, doesn't matter what you're taking the limit of a times b is equal to limit of a times limit of b. So you can do them separately, as long if it's multiplication. Does that make sense?
Yes.
Okay. Did we have one more unresolved one or no?
No.
That was it?
Yeah.
That was it? Okay. I have this one now for you. I want us to give this one a little bit of thought. That's n over e. Yeah, this is the same as sum n over e to the n. Those are the same things. So let's take a minute to go through this one. Nth term test. Nth term test. What about the nth term test here? If we just take the limit of this thing right here by itself, you get infinity over infinity. If you do L'Hopital one time, you're going to get 1 over e to the n, and that's going to go to 0. It tells you nothing. Is it geometric? You have n as a power, but then you have n on top. Geometric doesn't work that way, right? Geometric looks like a/r to the n minus 1. This is a constant, right? It's not n. That'd be great if it was, but it's not. So it's not quite geometric, okay? It's not telescopic. It's not harmonic. It's not a p-series. Compare. What do you want to compare it to? I'm going to try a limit compare.
Could you just leave it as 1 over e to the n?
1 over e to the n? I like that one.
Because
So if a sub n is n over e to the n, why don't we compare it to 1 over e to the n? Now that's because when n gets big, this dominates that, right? Like the n on top really doesn't matter much, does it?
right.
Now, but you need to know what 1 over e to the n does. So what is the series 1 over e to the n?
Is that technically a p?
Not p, because for p series, the n is the base,
Oh, right.
and the p is the power, right? It's not p series, but it is a series you should know. It's geometric. So we need to rewrite this like this. That's the same thing, isn't it? Because this is a 1 up here, you could have said that that's 1 to the n. And then they're both to the n power, because 1 to the n is still 1. So this is equivalent to that, right? And then you could make that minus 1 plus 1 and then move an a out in front, couldn't you? It's just a weird number, right? 1 over e is just kind of strange. But this is geometric. Can we leave it like that? We are not being asked what this converges to. We just need to recognize it's geometric. Do we all recognize that that's geometric? Now, does it converge or diverge? That we do need to know. What is R? What? I didn't hear that. What? R is 1 over E. And E is about 2.718 something. So 1 divided by 2.718, that's going to be less than 1. And that means this converges. Agreed? All right, so at this point, we have a candidate for something to compare it to. It's a convergent geometric series. So we have two options at this point. We can do the inequality thing, or we can use the limit comparison, right? It's our choice. Y'all want to try the limit comparison? That seemed to work pretty good. So let's do the limit comparison. I'm going to do it up here. If I do limit comparison, I'm going to take the limit as n goes to infinity of the a sub n over e to the n over b sub n. I'll just write it this time because it's not that hard to write that. That's what I'm trying to take the limit of, right? A sub n over b sub n. And then we flip it. And when we flip it, what are we left with? Just n, right? Uh-oh. That goes to infinity. What does that mean? Failed. Okay, failed. So that failed, didn't it? All right. Well, maybe we could get it the other way. Instead of doing the limit comparison, what about just the straight up comparison? That means I'm not going to do the limit, I'm going to do the inequality instead. So if this converged, what do I need to show? I want to show that a sub n, that one, is smaller than or equal to b sub n, right? So I'm using the same comparison. So if I do that, I've got n over e to the n. I need to show that that's less than or equal to 1 over e to the n. And multiply both sides by e to the n. N is less than or equal to 1. Wrong. Fails. So what the heck do we do? What other tests do we... Okay, so we have a couple options here. We could try a different comparison, right? Which I would challenge you to find one. I don't think you're going to be able to find one to compare it to that'll work. So basically we've exhausted... Let's see, the nth term, we already did that. It's not geometric, right? This is not geometric. It's not a p-series. We've tried the comparison. Nothing worked. The thing we haven't done is the integral test, right? Do you agree? We haven't done the integral test, and that's what'll get it. Because you can integrate this. If you had to integrate that from 1 to infinity, you'd basically be integrating x e to the negative x dx, and you could do integration by parts on that. And that will, if you do it, converge. I'm not going to show the work. This is in your homework. Okay, this is a homework problem. Actually, the homework problem, I think, has 3n right there, minus 3n. But I guess the moral of the story here is this, and what we've seen so far in this section, is that the reason we have a bunch of tests is because every series is different. And sometimes one test is better than the other. If we had one test that worked for all series, then we would just teach you that one test, right? We've seen the limit comparison test. We've seen it work pretty well for us in the previous two examples. We saw the comparison test work pretty well, but we also saw it had weaknesses, right? The integral test, we used it last class. It sucks. It's a lot of work. And if we can do it with something else, let's do it with something else. But we can always fall back on that, right? So we got a lot of things at play here, don't we? And we're almost through this whole thing. We have still to talk about the ratio test, the root test, the alternating series test, and then that thing at the very bottom. So we have 4 more things to discuss, right? Right. Okay, so what we're going to do now is we're going to do the alternating series test. So we're going to move on. We are done with 8.3 now. You can do your homework theoretically at this point. I anticipate that you will have trouble with the homework which is why I provide solutions to the homework on video. All right? So I encourage you to go through all the problems that I assigned, if not more, and reference my videos when you get stuck, if you get stuck. When you get stuck. You will get stuck. Nah, you won't get stuck. All right. I'm sure my other class told me that they're done. They're exhausted. They're like checked out. Are you all there yet? Yeah. Like the semester. Thanksgiving is usually when the bottom falls out. So I think I try and illustrate this or try and stress this in the very beginning of the class. Like, you know, Cal 2 is this long marathon, and when we get to Chapter 8, this is when it becomes the most like. I guess we really have to think, and we're just now starting to tap into it right now, right? 8.4, we get to 8.5. 8.5 is titled Power Series, and that's when the fun starts. But I know everyone's running out of gas. The class doesn't care if you're running out of gas, right? The course just has to keep going, so keep that in mind. Yes?
Power series or how we can solve the like E?
Yes. Yep, that's where we're going. Well, actually, Power Series are going to start that, and then we won't do that until we get into 8.7, which is Maclaurin series and Taylor series. So, yep. Our goal is to get to that. All right, I'm trying hard, so that's why we're going to start 8.4. .4 Other convergence tests. Okay, now I will officially state this. If you go to your sheet here and you go to geometric, do it this way. And bring it up like this. Let's look at these. Okay, notice on the Nth Term Test, it gives us no conditions on the series we're looking at. It just says, hey, we have a series, right? For it to be geometric, it says, no, your series has to look like this to be geometric, right? Now, P series, it says, no, your series has to look like this to be a P series. Integral test says, okay, you've got to have a series look like this where you can switch your a sub n to a function, and then your function has to satisfy these positive and decreasing and all that crap, right? Look at the comparison test. I conveniently left out, bless you, I conveniently left out something that you had alluded to a little while ago. And that is, notice that if you're going to use the comparison test, which includes the limit comparison test, both of them are included in here, then the sequence in here and the sequence in here that you're comparing must be positive sequences. That means those numbers can never be negative. So that means if you ever have negative numbers inside your series, this test is off the table. All right? Now, I didn't stress that in the beginning because I want to wait till now. So comparison test is not acceptable for what we're about to do. So let's first define an alternating series. Okay, so what is an alternating series? That would be a series that looks like this. Remember, we're adding pieces up, right, forever? So it'd be something that looks like this. A1 minus A2 plus A3 minus A4, right, plus A5 minus ... right? That same thing. So it's like you add, subtract, add, subtract, add, subtract. Yep, it's going to have that negative 1 to the end. Or you could have something like this, where you have negative A1 plus A2 minus A3 plus A4 minus A5 plus ... So you're either going to start with a negative, then go positive, or you're going to start with a positive and then go negative. So in this case, this would be, it would look like this. It would be the sum n equals 1 to infinity. We would need negative 1 to what? And plus 1 would start us off at positive, wouldn't it? And then that piece right there just takes care of the switching of the signs, right? Then we actually have some formula that's going to give us the numbers. I'm going to call that formula B sub n. All right? It's like all of this together is A sub n, but this part that makes the sign switch, if we peel it off separate from this, we will assume that this right here is always positive. Does that make sense to you? I'm going to show you an example, all right? But what I'm getting at is when you look at an alternating series where the sign switches, you have the piece that makes the sign switch followed by a formula that gives you each of the numbers. So this one right here, what would this one be? There's only one slight difference in this series. You have -1 this time to the n, and then you still have some b sub n. And again, that b sub n is positive. That's what so all alternating series look like one of these, okay? Now here's an example of an alternating series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus dot, dot, dot. That is an alternating series, isn't it? Okay, can you give me the formula for this? So n equals 1 to infinity, -1 to the n plus 1 because it starts out positive, and then just 1 over n. So do y'all see what I'm saying? Like, this part right here is the part that gives you the numbers. And then this part right here is the part that makes the signs switch. So that 1 over n is always positive. Got it? Let me give you another example of an alternating series. Another example. How about 1 minus a fourth plus an eighth minus a 16th plus 32nd plus minus dot, dot, dot. Okay, so sum n equals 1 to infinity. It alternates, right? So -1 to the n plus 1 again, right? Because it starts out positive. Now the formula, the thing that gives you the numbers, I heard it, is what?
1 over 2 to the n.
1 over 2 to the n. It's close. -1, n minus 1. Because when you plug in 1, you need to get 0 so that you get 2 to the 0, which would give you this one. So this one is 1 over 2 to, whoa, wait, hold on. I'm missing a 1/2. Yeah. Hold on, I'm missing a 1/2 in here. Okay, so look, no, you know what? I kind of unintentionally did that, but I can fix it, okay? So watch. Here's what I'm going to do. Do y'all realize this is not it? Yeah. Because I'm missing a 1/2 up there. Okay, so let me tweak it. Here we go. This is what I'm going to do. I want you to understand that from here on, it was good, wasn't it? Yeah. So that's like 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, right? Yeah. So watch. And this, I'm not doing this like, oh, I'm just fixing it to fix it. Later on, you might have to do this for a problem down the road, all right? So you may see this again. 1, that's the only piece that doesn't belong here, right? 1 plus, here we go. Sum, n equals 1 to infinity. Now, it's going to start out at negative this time. -1 to the n. So what I'm doing is I'm just peeling that 1 off the front. It's 1 plus whatever this sum is. And then that's going to be 1 over 2 to what? This time I want to start out with 2 squared, right? Yeah. Then 2 cubed plus 1. There we go. I fixed it. The idea is this. What if this converges? What if this series converges? That will converge, right? Because that plus 1 is still a number. What if this diverges? Then that plus 1 will diverge because adding 1 does nothing. Okay? All right, so I just saved my ass there. Okay, let's now move on. How do we figure out if an alternating series converges or diverges? Yeah, we have a test for it. We have something called the alternating series test. And it's a really nice test because it's pretty easy to implement the test. Right? It says, suppose you have a series, and that series is actually an alternating series like this. Now, I intentionally did not put here plus 1. It could be plus 1. Just understand that this part right here could be that or that to the n plus 1. Are you all okay with that? That just controls the alternating. So let's say we've got this. Then this converges if the following two conditions are held. First of all, we need b sub n to be greater than or equal to b sub n plus 1. And the next one is that the limit as n goes to infinity of b sub n equals 0. That's it. Those two conditions are the only conditions that we need. So what does this mean? What does this mean? Decreasing sequence. So basically, and notice we're looking at b sub n, right? Which is only that piece that's positive, not the negative switching in there. As long as this is decreasing, right, the nth one is bigger than the next one, which is bigger than the next one, which is bigger than the next one, so they get smaller. And then this says that this goes to 0. Then we're done. So let's go back and take a look at this example. This is a classic example here. Most Cal 2 students will see this. What series does that look like? It's not, but what does it look like? It looks like 1 over n, right? So doesn't that look like harmonic? It's not a harmonic, though. It's like an alternating harmonic. We know harmonics diverge, right? I wonder if this diverges or converges. So let's see. We rewrite it as the sum n equals 1 to infinity of negative 1 to the n plus 1. We already established this, times 1 over n. So we did that a second ago, right? So b sub n for us here is what? 1 over n, right? Okay. We have to establish the following things. I want to show, first of all, that b sub n is greater than or equal to b sub n plus 1. I think that's strict. Is that strict? No, it's not strict. So how do I show this? Do you remember how to do this? We did it with our bounded monotonic sequence theorem way back when. Yeah, you're just going to first write b sub n, which is the left side, 1 over n, greater than or equal to, and then just replace n with n plus 1. So 1 over n plus 1. And this is a question. Is this true, right? So just kind of like cross multiply, you get n plus 1 is bigger than or equal to n. Cancel the n's on both sides. 1 is bigger than or equal to 0. That checks out. Cross multiply. I have not told you how much I hate using the terminology cross multiply. I haven't explained. I use it because most students understand what I'm talking about, but I absolutely hate using it because it really doesn't. Cross multiplication only works when you have a single term and a single term on both sides. Like if you had a +2 here, like you can't do it, okay? So I think students lose sight of what they're actually doing here. When you're cross multiplying, you're multiplying n plus 1 here, n plus 1 here. Multiplying both sides by n plus 1, which makes these cancel, right? Then you're multiplying both sides by n, which makes these cancel. So n times 1 and then 1 times n plus 1, which really does look like you're just cross multiplying. But you're really clearing fractions is what you're doing. Yeah. Yeah, it's just like the actual terminology, cross multiplying, is not math terminology. Like we use it, but it's not like most math people don't like using that. We use it only because the students understand it that way. All right. So are we done? What? Huh? No, we still have to show a second thing. And look at the second thing we have to show. And this is like good old days. Check this out. We're just going to take the limit as n goes to infinity of that, right? 1 over n. And that goes to 0, right? Now, keep in mind, the nth term test, right, tells us that if the limit of this goes to 0, right, the test fails, right? The nth term test. But if it's an alternating series and we split off the piece that's not alternating and that goes to 0, that actually does tell us something if it's an alternating series. It tells us that it's going to converge, but we also must have this condition of decreasing maintained. So we're done. It converges. Harmonic series diverge, alternating harmonic converges. Yes?
So if one of these failed, then it automatically diverges?
Oh, I'm glad you asked that. I had a student in the other class ask the same thing. So if one of these two fails, then the pregnancy test is bad. Inconclusive, fail test.
So
Yeah.
this test doesn't tell you?
No, you would probably move on to the next test after that. The next test is the almighty ratio test, which we won't cover today. But that to me that's my favorite test on the page. And you'll see why when we get to series. You'll see why the ratio test is so awesome. Okay. All right, so let's see what other example I want to do here. How about this one? Does this series converge or diverge? How am I doing on time? 7 minutes? Yeah. Okay, 7 minutes. How about -1 to the n times n squared over 3n cubed plus 1? That look familiar to you? I did that one earlier, didn't I? But without the alternating part. So first we recognize it's an alternating series, right? So all the other tests, like the comparison, all that, is off the table. But I can use the alternating series test. I'm just going to say AST from now on, alternating series test. And I need to show two things. First thing I need to show is that b sub n is greater than or equal to b sub n plus 1. Ooh, crap. Do I really want to do that? Do I really want to try and show that n squared over 3n cubed plus 1 is greater than or equal to, I have to plug n plus 1 into that, right? That's what b sub n plus 1 means? So do you really feel like doing this? So do you understand there's going to be a little algebra there, right? Yeah? We agree? Could we do it? Maybe, huh? What did I say?
Yeah, there's what algebra?
There's going to, I don't know, there's going to be some algebra there?
Oh.
Yeah, I think that's what I said.
Yeah.
It's going to be algebraically, you heard something completely different?
Yeah.
Okay. You want to share what you heard or no?
You said real algebra?
Oh, okay. There's going to be some algebra there. We could mess with it, all right? But let me just ask you something. Is there another way that we can show that something is decreasing? A function is decreasing. How? Yeah, over time, I guess you could. But I'm asking you to think abstractly back to calculus 1. Take the derivative, and if the derivative is negative, you are decreasing, aren't you? Now, this is a sequence. So derivatives are off the table unless we look at that as a function of x. If we look at that, so I'm sitting here going, I don't really feel like doing this. Like, I'm not happy about that, right? So what I'm going to do real quick instead is just consider the possibility that if I look at that as a function of x, that if I can show that the derivative is negative, that it's decreasing, right? What would you rather do? Would you rather play with the algebra here or take the derivative? And that's a personal question you have to ask yourself. I personally would like to just take derivative of that. So if I take derivative of this,
Would you have to state like let b of n equal f of x?
I'm not going to, but yes, technically we are saying we're switching this over to a function of x.
Okay.
But I think when we write this down, it's understood that, yeah, I know what you're doing. Yes?
So on the exam, would I have to switch it over and show them switching it over? Or just
Instead, what?
like,
Like,
let,
no, if you just wrote this, that would be fine. Are you saying leave it as ends
like
and
at
take the
this point,
derivative?
At this point, I don't have to say that.
You don't need to say it. No.
Okay.
Yeah, I understand what you're doing. At some point, we have to, like just, like we get it. We know what's going on. Yeah. Okay. So 2x times 3x cubed plus 1 minus, what's that? 9x squared times x squared all over 3x cubed plus 1 squared. So I'm running the quotient rule on that, right? And maybe you're not too happy about that.
No.
You're not? Did I do it right? I think I did it right. I just need to show you that this is negative, right?
Yeah.
Well, negative whenever x is bigger than or equal to 1, because n is 1. So that may not look that appetizing, but let's just continue. This is going to be 5x to the fourth plus 2x minus 9x to the fourth, right? On top? Just distribute through. 6, yeah, ooh, what?
Yeah.
I'm getting too close to Thanksgiving, I guess. I just added 2 and 3 together. Wow. I'll get like 10 lashings for that when I go to math hell later. Okay. 6, and then this is always positive, right? That's always positive. So I don't care about the bottom because it's always positive. That has no impact on anything. And now when I simplify the top, it's 2x minus 3x to the fourth. Y'all agree with that? Over a positive number. I'm going to go one step further. I'm going to factor an x out and be left with 2 minus 3x cubed over a positive number. Are you convinced that this is negative? As long as x is bigger than 1, right? If x is 1, of course, that's going to be 3, and that's 2 minus 3. It's negative. This right here is a positive number right there, right? That's positive. So these don't matter. So all that really is determining the sign of this is this. So I'm checking that off. It's decreasing. One more thing to show, and I'm done. And this is the part that I need to take the limit as n goes to infinity of just this piece right here. And it is 0, in fact, when you do L'Hopital. All right, so this series converges. All right, we're out of time for today. There's still some things to do here in 8.4, significant things to do. So for now, I invite you to have a good Thanksgiving and do all the work for Chapter 8 that you haven't done. Make sure you get all your homework. You've got the whole nice long weekend. Well, actually, it's no different than any other weekend for us, huh? Now you have less time.